Hello everyone, so let's look at another example on acids and bases, and in this example we're looking at an acid-base reaction. So we're told to calculate the pH of the solution that results from mixing 50 milliliter of a 0.14 molar formic acid and 25 milliliter of a 0.28 molar sodium hydroxide solution. Alright, and we're given the Ka for formic acid. So first let's analyze what's going to happen if we mix these two solutions. So of course formic acid is an acid. We're given a Ka for formic acid, so it's an acid, and sodium hydroxide is a strong base. So we expect these two things to have an acid-base reaction, or these two solutions to have an acid-base reaction, and sodium hydroxide being a strong base, we expect it to be a strong product-forming reaction. So if we write it the formic acid, right, so HCO2H, it's a solution, aqueous solution, plus sodium hydroxide solution should be strongly product forming. And because the formic acid is the acid, it donates a proton, so it gets deprotonated, HCO2 minus aqueous plus the sodium hydroxide. So technically, I mean, the sodium should go here. My apologies. So aqueous, the cation, the sodium anion or sodium cation neutralizes the anion, the formic anion that forms there, plus water, right, is the other product that forms. Alright, so that is what forms from this reaction. If we want to write a net ionic equation for this, then we can just remove the sodium from this. So that means that HCO, or actually let me just leave it up here. So that means the sodium is just a spectator ion, so we can just make that a minus. Because hydroxide, the net ionic equation, that means it's just hydroxide reacting with the acid, right? So that's our net ionic equation. All right, so that's what forms. Now, because we are asked to calculate the pH, we need to determine what is the species that's going to dictate the pH. So let's first analyze whether or not there's any of our reactants in excess or are limiting. So let's first determine the number of moles of the formic acid. All right, so CHCO2H multiplied by the volume. Right, so the number of moles is equal to the concentration times the volume. Remember, the volume needs to be in liter. We're working in molar, so and I got a value of 7.0 times 10 to the negative 3 mole formic acid. And we're going to do the same for sodium hydroxide. It's going to be equal to the number of the concentration of sodium hydroxide multiplied by the volume of sodium hydroxide. And you should also get a value of 7.0 times 10 to the negative 3 mole sodium hydroxide. All right, so because this is a one-to-one reaction, right, it means there is no limiting reaction or limiting reactant. And there's no excess reactant as well. Alright, so our attention must hence turn to, because both of our reactants are consumed, that means the pH must be dictated by the product. And I mean, I don't know about you, I didn't think water's pH is 7, so that means the pH of the products, we must only consider that the formate anion to be of consequence here. And the formate anion is the conjugate base of formic acid, right? So formic acid has a Ka value of 1.8 times 10 to the negative 4. So that means the formate anion must have a Kb value. So interestingly, so that means Kb of HCO2 can actually be calculated from the Kw value, right? And hence it will have an effect on the pH. So that is where our attention must turn to. So if we calculate that, 10 to the negative 14, and this is divided by 1.8 times 10 to the negative 4, we get a value here of 5.55 times 10 to the negative 11. Therefore, the pH is dictated by the formate anion and is slightly basic, right? Because it has a Kb value. Very small Kb value, but expected to be slightly basic. And slightly basic according to the following equilibrium. So we expect the formate anion to react with water to form the following equilibrium. It should form formic acid again, and hydroxide anions, which of course is the thing that will dictate the pH. So if we can determine the number of hydroxide ions at equilibrium, we are able to calculate the pH. Alright, and how do we calculate the number of, or the concentration of a species at equilibrium given the initial concentration of an acid or base? Right, we use an ice table. But of course, we first need the original concentration of that acid or base. So we first, actually to calculate that concentration, we first need the number of mole of this species after the reaction, after the initial acid-base reaction. And we can get that from the amount of formic acid, H, and we see it forms in a 1-to-1 relationship from our HCO2 minus. 1 mole of HCO2 minus forms from 1 mole of HCO2H, right? That's according to our reaction equation. So that means that we also have 7 mole times 10 to the minus 3 mole of the formate of HCO2 minus that forms, and therefore the initial concentration of HCO2 minus is equal to its number of mole divided by the total volume. And this volume, of course, we must calculate from the total volume that is added together. So we mix 50 milliliter with 25 milliliter. So that means it is 75.0 times 10 to the negative 3 liter. This is of course in mole. So that means I get a value here of 0.0933, etc. molar formate anion at the start of this equilibrium. Right, now to get the concentration of the hydroxide, to calculate the pH, we of course need an ice table. So I've gone ahead and drawn out the ICE table. Of course, initial, change, equilibrium, all in molar quantities. So I've written down our initial concentration of 0.0933. Water doesn't participate, its concentration remains constant, so it does not participate in this. And then we have formic acid that forms, and the hydroxide anion they don't have initial concentrations, right? Because they're not yet formed. Now, to determine the change, to proceed towards equilibrium, we expect our concentration of our reactant to decrease and our product concentrations to increase, right? We can see that from the reaction quotient, which is 0. So that means the forward reaction is favored until we reach equilibrium, right? And for water, we expect no change because of its fugacity, it should not change. All right. So therefore, at equilibrium, the formate anion should have a concentration of that minus X. The water is not applicable, and each of the products should have a concentration of X. All right. So now, how do we calculate these equilibrium concentrations? Well, we of course can use the Kb value that we calculated for the formate anion. Just want to move this up a little bit. So we remind ourselves how to write a K expression. So Kb, which we calculated at the top here, was 5.55, etc., times 10 to the negative 11. And that should be equal to, if we look at this equilibrium that we have here, is equal to the formic acid concentration at equilibrium multiplied by the hydroxide concentration at equilibrium. Right, that all divided by the formate anion concentration at equilibrium. Looking at our ICE table, we see we denoted this values of X and X, and this has a value of 0.0933, etc., minus X. We can simplify this a little bit by saying this is X squared divided by 0.0933 minus X. All right. As usual, this is a very small k, so let's check whether or not we can make an approximation. So k, so this is a kb times 100. In this case is 5.5 times 10 to the minus 9, so that means it's 0.1, 2, 3, 4, 5, 6, 7, 8, 5, 5, 5, etc., which is much less than the initial concentration of that, right, which is 0.0933 molar. All right, so that means we can make the approximation. X squared divided by 0.0933, etc. Cool. So let's solve for X. All right, so multiply each side with 0.0933 and take the square root, and then we get X. So I get X as, and of course X, let's just remind ourselves, X is actually the hydroxide ion concentration at equilibrium, right? So then we don't have to write that again. That is 2.27 times 10 to the minus 6 molar. All right, and because we know the hydroxide ion concentration at equilibrium, we can calculate the POH, which is equal to negative the log of the OH concentration. I know I never write the equilibrium here, but I mean it's implied. This gave me a value of 5.64, etc. And from that, we can get the pH, because pH plus POH is 14, so So that means pH is equal to 14.00 minus pOH, which we need to round to, let's check, two significant figures, because Ka and the formic acid, everything, there's two significant figures right through here. So that's 2 decimal places for the pH, 8.36. All right. And that is basic. That is larger than 7, and so it's basic as we expected, all the way up there, so that everything forms a nice continuous loop. All right. Cool. So that's again the pH after an acid-base reaction took place. There was a stoichiometric mixture, and then the pH was dictated by the product that was formed, the anionic product that was formed. So importantly, you need to check stoichiometry beforehand and then determine what species will actually dictate the pH. Always remember to check that. Right. Thank you for watching. I'll see you in the next video.